One final example of being able to evaluate a trigonometric substitution problem by completing a square. A little bit different than the previous problem that we just looked at. So we have dx over the square root of 21 minus 4x minus x squared. And the reason it's different is because this time we have negative sign in front of our x squared coefficient. So what we're going to do is we're going to rewrite this. And remember, the trick is to take half of the middle coefficient, square it. So that's going to be negative 4 over 2 square, which is going to be 4. But we're going to have to be careful when we try to rewrite this. All right, so let me show you the trick to rewriting this one because of all the negatives that are in there. All right, so we're going to have to add and subtract 4 to be able to make this work. So what I'm going to do is I'm going to rewrite this as the integral of dx over the square root of 21 minus x squared minus 4x minus 4 plus 4. All right. And the reason I write it as a negative first is because I know I'm going to have to factor out a negative from all of these terms to be able to factor it. All right. And so that might be a trick to remember, is that if the first term or the quadratic term's negative, then you're going to have to factor a negative out anyway to be able to factor it nicely as a perfect square. So it might be better just to try to write the negative with the completing the square component of the problem. All right, so I'm going to add the 21 and the 4. I'm going to factor out a negative. And so now this becomes integral of dx over square root. Now I really like 25, and I'm going to factor out a negative from these 3 terms. And that's going to give me x squared plus 4x plus 4. Now we could just factor this as a perfect square trinomial, and that's going to turn into the integral of dx over the square root of 25 minus x plus 2 squared. Now we can start employing the tactics to be able to evaluate this using the trigonometric substitutions methods. All right. Now let's start by saying u is going to be x plus 2 and du is going to be dx. And so what that's going to do is that's going to put it really nicely into the form that we need. All right, so now this is going to be the integral of, instead of dx du, over the square root of 25 minus u squared. And now we can go ahead and do our trigonometric substitution. All right, so let's let u be equal to 5 sine of theta. All right, and I think it's pretty clear to everybody that a is going to be, h squared is 25, so a is going to be 5. We're going to have our u over 5 to be equal to sine of theta. Our derivative of theta is going to be 5 cos theta d theta. So that's nice and easy. And it may behoove us in this problem to get the arc sine of u over 5 for theta. So arc sine of u over 5 equals theta. We're going to construct our triangle. And going back up here, sine is the opposite over the hypotenuse. So in this case, this is u. This is our hypotenuse 5. And then we could just use our Pythagorean theorem, or again, we could just look at what it is that we're trying to rationalize or get rid of the radical for. And so either way, we're going to end up with 25 minus u squared. All right, so I believe we're now set to perform all of the substitutions to get to our evaluation. So now in terms of theta, we know that du is going to be 5 cos theta d theta. And then under the radical, this is going to be 25 minus 5 sine of theta squared, right? Just by substituting for u and for du. Now we're just going to work on the radical as we did the other 5 problems. So if we do so, square root of 25 minus 25 sine square theta, factor out of 25, 1 minus sine square theta, We'll use the Pythagorean identity, 25 cos square theta, use algebra, 5 cos theta. All right, so where we see this radical, we're going to substitute 5 cosines of theta. All right, so our new integral is going to become 5 cos of theta d theta, and then we just showed that the denominator is also going to be 5 cos of theta. And so we reduce this and we just get the integral of d theta, which is really nice. We know that the antiderivative is going to be theta plus c. And this is a problem where it was good that we were able to go back and solve for theta in terms of u. So theta is our arcsine of u over 5 plus c. And then the very last thing we have to do is remember that u was x plus 2. So remember all the way back up here, because we had to do the completing the square, that u is equal to x plus 2. And so we end up with the arcsine of x plus 2 divided by 5 plus c. And that should be the most simplistic answer that we can get out of this. All right. Of course, if you want to verify your answer, you can find the derivative of this. And that's not too bad to find the derivative of, but you'd have to do a lot of manipulatives to get back to this animal right here, okay, the original integral. All right, so lots of problems involving our trigonometric substitutions, not easy problems, okay, but do well with your bookkeeping, okay? Have a list of your trigonometric sort of identities next to you. And the other thing I would suggest is, as you're doing this, to try to make sure that at the end of the problem, use your triangle to back substitute.